welcome back to the physics video lecture. This is Physics 4B video lecture 7. We're talking about heat engines. And I'll do a bit of a review on the heat engine and then we'll work our way through the efficiency. This time I have a homework assignment for you. So heat engines. And while we're at it, we'll be able to talk about heat pumps and refrigeration as well. But first we'll start with the heat engines. The idea is to take thermal energy. For example, fuel has so and so many calories per gram or kilojoules, whatever units you want to use per gram. And we want to obtain useful work. In driving a car, doing other things like that. So we also know that we have, and I like using this calorie for this reason, 4,186 joules. The idea being that we knew that via friction we can do so and so much work and raise the temperature of water by so and so many degrees. Okay, so we knew we could do this. So let's get the arrow to the left here. But can we take thermal energy and get a certain amount of work out of there? Well, it turns out we can. And so, like numbering things here. So the next point was that we had a couple of working heat engines. I showed you that little steam engine. I talked about the Christmas pyramid. Hopefully you guys looked it up. And I'll draw those again. So the Christmas pyramid has candles down here. Okay, there's a flame burning. And due to the convection current of the hot air going through here, you actually can get some mechanism to spin around. Okay, so this was the Christmas pyramid. And then we also had the steam engine, where we had a boiler with water inside, flames here on the bottom, piston, connecting rod, flywheel, and I showed you how by burning the fuel here we got the thing to spin and the light to go on. So those were our example heat engines. Now there's one demonstration I like to do. I'm just going to describe it to you. I'll put this as a note for the Christmas pyramid. To get this thing to really spin fast, you can use a chimney. So the chimney effect on the Christmas pyramid is I have this big cardboard chimney, okay, and by encasing this system in the big cardboard chimney, what it does is it separates the higher temperatures and the lower temperatures, and it gives a really good airflow. It turns out also that you've got a high temperature in the boiler and you have a low temperature. How about we use blue? You have a low temperature. You know, we had a valve releasing steam to a lower temperature atmosphere compared to the temperature in the boiler. So this is one of the keys to the heat engines, is that you need a substantial temperature differential. You need a high temperature and a low temperature. So fundamentally there's a heat flow going on, and we know that energy flows from hot to cold spontaneously. Good, so this was the reason we're doing it. We want to get work. These were some of the mechanisms that do it. I'm going to describe a couple other mechanisms later on in the hour. Chimney effect is very important here. Okay, so this was the Christmas pyramid, this was the steam engine. I'll just write that down again for you. Steam engine. by the way, this is an external combustion engine. There are the engines in our cars are internal combustion engines. So internal versus external combustion. Maybe I'll say a little bit more about that. So for the external combustion, we are burning the fuel here and applying the flame to the boiler and heating up the water inside the steam and so forth. The internal combustion is you have there's the cylinder, it's got the piston inside, connecting rod. There's a spark plug or a glow plug. You're actually injecting fuel into this space here, and the combustion, the little explosion occurs right here. The expanding gases push the piston forward. Okay. So internal combustion, fuel is injected, then ignited. But still a heat engine, obviously. Okay, the next thing we have to do is develop a schematic diagram of the process here. And this is very standard. It's in every book that was ever written, so to speak. So let's call this the schematic diagram for the heat engine. And this is very stereotypical, so I'm just going to draw some boxes and arrows, and then we'll discuss it. We'll label it and discuss it. Good. There's the boxes and there are the boxes and arrows. So what we have here is what's called the high temperature reservoir. High temperature reservoir. This is the source of a certain amount of heat, which we're going to call QH. So that's thermal energy at T equals TH, and it goes to the engine. So this is the engine. And the engine, if you're lucky, does some work. So that was our goal, right? That was our goal. We had this thermal energy and we wanted to get some work out of it. There we go. Okay. For example, in the heat engine here, we had some thermal energy, push the piston forward, turn the wheel. There's our work. Okay. Force times displacement. Pressure times area is force, times how far this goes is displacement. There's our work. But in order to get a cycle out of this, we have to bring the wheel back to its starting point, which means the piston has to go to the left. And in order for that to happen, the valve has to open and eject some of that steam, that hot air, that hot gas into the atmosphere. And so that is what's going on right here. We have thermal energy at a lower temperature going to what we call the low temperature reservoir. In my example up there was the atmosphere. Okay? So low temperature reservoir . Good, so that's necessary to actually have a cyclic process. And if you look at the Christmas pyramid, you know, we've got the high temperature reservoir down here, and we're getting that convection current, okay? So that energy is flowing past the blades of the turbine. It's spinning around doing some work. When it comes out the top, the temperature is lower. The upper atmosphere there is the low temperature reservoir. And again, we obtained some work of that. So that's the schematic, and we have two temperatures involved, a higher and a lower temperature. We have two energy quanta, okay? The thermal energy at a higher and the thermal energy at a lower temperature, and we have the work that came out. So we're going to analyze the schematic diagram next. So we're numbering things, are we? This is 4. Analysis of the schematic of the heat engine schematic. So the heat engine. So now we're going to idealize the thing. So it's going to be an ideal engine. And the idealization is saying that this is all that's going on there. Okay. These energy quanta are all that we have. These two temperatures are all that we have, and this is the work that's coming out. So if it's an ideal engine, there's no friction somewhere, there's no heat leaking out elsewhere, right? These are the heat transfers, and this is the amount of work being done. So we have the ideal engine, no other loss. I'll just write no other losses, okay? And the other thing we're going to assume is energy is conserved. This is the famous first law of thermodynamics, which takes various forms, but most general, it's just energy is conserved. So what does that mean in the case of this engine? These are the only 3 energy quanta, right? QH, QC, and W. So what that means for our case is QH equals QC plus W. Okay? We had energy at a higher temperature. We got some work out of it. We have energy at a lower temperature. So energy in, energy out. That's one way to look at that. Anything else? Yes. The third point here is that entropy of the entire system, entire isolated system, delta S total greater than or equal to 0. And remember, that just means that, well, not just means, but that is consistent with energy flowing from the higher to the lower temperature, as we have right here. See this, whatever this output in terms of work, there's no friction involved, there's no heat, there's no thermal energy involved with that W. That was one of our idealizations. Okay. So that's what we have. Entropy of the entire isolated system is greater than or equal to 0. And then I should say that this is one of the reasons to discuss these, to bring the reservoir in. We're thinking the whole system includes the 2 reservoirs. So we're going to apply the entropy theorem to that system there. And I'll just remind you again. Delta S total greater than or equal to 0. That is, I'll remind us of the picture there. We haven't done this for a couple hours, but it'll all come back. The idea was that we had TH, Q, PC, right? That's what this meant. And I proved it originally with a very simple analysis of this isolated diagram here in terms of the entropy. So yeah, we're going to apply these things. and discuss the efficiency. What's the maximum amount of work that we would be able to obtain in this engine here? Good, so that's been set up. All right. Okay, our next question, what's the maximum amount of energy that can be obtained? Numbering these things 5. What is the max amount of work that we can get out of this engine? And the idea is we're putting in QH, that's after all, that's the amount of energy in joules, okay. And how many joules of work can we get out? Okay. So we have to define the efficiency. And that will be defined as the work output divided by the thermal energy input. So this is always the definition of efficiency. Now the ideal efficiency involves the fact that we have energy being conserved right here. So the ideal efficiency for this engine, I'm just going to use the same letter, would be taking the W being equal to QH minus QC. Okay, W equals QH minus QC. So I have QH minus QC divided by QH. And then we can also call that 1 minus QC divided by QH. So this ideal efficiency is under the assumption that we have energy conservation with, among these 3 quantities. And you can see efficiency has to be less than or equal to 1. 1 is 100%. 1 would be all of this energy going into work. And of course, the 100% efficiency would mean there is no Q sub C. Okay. But we're going to see that's not possible, right? There will always have to be Q sub C. That was actually already when we discussed the cyclical nature of these things, and the fact that the thermal energy is flowing from hot to cold. Good, so that's the ideal efficiency. 6. Now comes the entropy analysis. So here I'm just going to write E ideal equals 1 minus QC over QH. And conservation of energy. Conservation of energy. Okay, so then we have that. Now, we're going to use the analysis of the entropy. So what have we done so far? We've used the energy as conserved right here, postulated this, that actually implied the second line. Now we're going to use 0.3 right here. So delta S total greater than or equal to 0. So what is delta S total for this process here? I'll put, and then there will be delta S total. It's going to be delta S for this process right here. Okay. Well, let's call it for the H. Then there's delta S for the work, because that's another process that's going on, the cyclic work process. And then there's delta S for the Q. For the Q sub C, so I'll call that C. So those are the three places where we can have a change of entropy. The energy being given off from the high temperature reservoir, energy doing its work, energy being given from the low temperature reservoir. However, this is an ideal engine, and this one is going to be 0. Equals 0. Why? Ideal engine. No friction, no heat's being given off by this engine. No wear and tear. Every time it completes one cycle, it's exactly the way it started before. That means there's no disorder. There was no increase in disorder in this engine because it's a perfect engine. It cycles, and then it, does say for example with the steam engine, it does one complete rotation. It's back to the way it was before. Okay, so for that reason, this is a 0. The delta SH. I'm going to break this down a little bit more. Recall delta S is a delta Q over T in Kelvin. Yeah, maybe I should have brought that up a little earlier. So what we're making use of is this fact here. It's the amount of heat that enters or leaves. If the heat enters something, the delta S is positive. If the heat leaves something, the delta S is negative. And the temperature is always positive because it's a Kelvin temperature at which that process occurs. Okay, we're going to go directly under this with number 7. So if you look in your notes, you'll see where I did this for this little drawing here. Right? And what we're going to do is very similar. Okay, 6, and here we are, 7. So now we have delta S total is equal to this delta SH, that is the energy flowing from the hot, so it's minus Q sub H, delta over Q, I just call it Q sub H, all right, no problem. Minus Q sub H over T sub H, okay? There's nothing going on with the engine there. And then we have this one. This time it's plus, and it's the heat going from Q sub C into T sub C. So we have plus Q sub C over T sub C. Okay. Now we're just going to say, well, that's greater than or equal to 0. That's the law, right? That's the law of nature, just energy flowing from hot to cold. So we're going to take this inequality here. Now we have, let's do this. Now we have QC over TC is greater than or equal to QH over TH. That's just the inequality I have right here. And we have QC over QH is greater than or equal to TC over TH. So that's simple. This is really the simplest derivation because I'm about to deliver the punchline right here. So now what is the maximum possible efficiency? So A. E maximum is going to be less than or equal to 1 minus, now, see, if QC over QH is greater than or equal to TC over TH, then 1 minus TC over TH is less than or equal to 1 minus QC over QH, okay? Just because of the direction of the inequality here, we're subtracting off something that's a little bit smaller, okay? 1 minus that. So here we go. E maximum is less than or equal to 1 minus TC over TH. So this is a hard and fast law of nature because it's based on the flow of energy from hot to cold. Okay, it's that general, and this efficiency has a name. If you give it the equal sign, then it's called the Carnot efficiency. But I'm going to write that down in a moment. Let's just notice what we have here. This was the ideal efficiency just based on the energy balances. Now, based on the fact that, nothing more than the fact that the energy flows from hot to cold, we have this inequality here. Okay. So we're going to have 1 minus QC over QH. That's equal to 1 greater than or equal to 1 minus TC over TH. Okay. So the maximum possible efficiency only depends on these operating temperatures. Okay. So if you're designing a heat engine, this will tell you how much conceivably can come out. You're still going to have to be, have a good design to even try to approach this. This is the highest. You're not going to get a higher efficiency. Let's do a couple of examples so we get an idea of that. So I'm going to write under here maximum, so 9 maximum possible efficiency. This depends on the temperatures that you're running, the ratio of these high and low temperatures with which you're running your heat. It's called the Carnot efficiency. So Carnot, very famous engineer, came up with this. Carnot efficiency, E sub C is equal to 1 minus TC divided by TH. Temperature, of course, in Kelvin. This is the simplest derivation of this, right? This whole thought process here, we did it number by, step by step. And yeah, you really want to understand what's going on here. So we'll just do a couple of really basic examples. A lot of complication in the details, but this is fundamental. Okay, I'm going to consult the clock before we move on. Very good. So our first example, we can just imagine a steam engine that operates between boiling temperature of water at atmospheric pressure and room temperature. Okay. So engine with pH is equal to 373 Kelvin, right? That's 273 plus 100 degrees Celsius. And TC is going to be room temperature, so that would be 20 degrees Celsius. Always convert to Kelvin, so that would be 293 Kelvin. So this could be something where you're boiling water and just having a jet of steam out into the atmospheric pressure, and it's turning a turbine. So my Christmas pyramid, for example, instead of the candles, we would maybe mount it horizontally and put it in front of a tea kettle. Okay. Here, I'll even draw something. So we've got a tea kettle here, and there's a bunch of hot steam shooting out here, and then we have our propeller somehow hooked up to whatever. Okay, that would be an engine that would be running between these temperatures. The maximum theoretical efficiency now, P carno, would be 1 minus 293 over 373. And of course, this was an 80-degree temperature difference. So you could also say it's 80 over 373, so that's 20% or something like that. Realistically, you could be running at much hotter temperatures. It's difficult to have the TC be all that low. Okay. Be that as it may, there's an example of a number, and we'll have a couple other numbers in the homework sets. Let's see what else. Yeah, you can make up other examples to your heart's content. Okay, this is how you do it. Dot, dot, dot. 22% or something. Put it in the calculator. Okay, so those are some examples of the Carnot efficiency. Now I should get you set up with a homework problem. We have a few, and they're going to be pretty much related, because the homework problems I assigned are all going to deal with these quantities here, the definition of the efficiency and the definition of the Carnot efficiency. Okay. So yeah, I may as well put that in right now. Numbering things, 10, 11. So I'll just give you some reminders before I assign the homework, and then I'll do a couple other little topics here. So 4 homework problems. For homework problems. I just erased that schematic, but what we're always looking at is QH, if it's ideal, equals W plus QC. Efficiency is always W over QH. So whether it's ideal or not, if the work you got, if they tell you got so and so much work out for such a temperature, then there's the efficiency. If that's not the ideal efficiency, that's just the efficiency per se. And then you've got the Carnot efficiency is equal to 1 minus TC over TH. Now, good, that's basically what you need for a lot of the heat engine problems. But if they talk about power and not just energy quanta, you also have to note for power, you're talking about power is energy over time in some form. Okay. So that'll be in addition to these if you're talking about power. And if you need time for one cycle, you can solve this for time, and you'd have time as energy divided by power, and so forth. Okay. So yeah, this is the one you have to bring into play. Now, one of the problems is about a power plant that's cooling into a river, and so there are also some flow rates involved in terms of the amount of water. So that'll actually, that one with the power plant will take you into the question of Q NC delta T, if there is, in that particular problem I'm thinking of, there's a maximum allowed temperature increase in the river. Okay, so your river, you're not allowed to heat it up too much, it causes ecological damage. Okay, so then you're using this quantity here. You could also have and I haven't done this one yet, but just it comes to mind. You could have dq dt. So this would be a certain amount of power again, of a certain, amount of, say this is the QC, this is the Q that's heating the river, that's going to the low temperature reservoir. You could have a dq dt of this form, dm dt C delta temperature. That would be the case where this is actually the mass of water that's carrying away the heat. This would be a flow rate. Flow rate in kilograms per second of fluid. So these kind of things would come into play as well. I think all 3 or 4 of these problems are pretty interesting, and they're really being done at the basic level here. So I think this is the simplest way of understanding a really interesting topic, efficiency of heat engines. This was just derived by the fact that energy flows from hot to cold. Okay, I'm going to consult the clock again. So what I want to do next is talk about some other heat engine projects that exist these days. You may have heard of them. So heat engines. The first one is called the solar chimney. And the second one is called the solar thermal power plant. And these are more, I wouldn't say theoretical, kind of pilot projects. This here we have major examples of on the way out to Las Vegas. There's some of these even over in Kalinga. So yeah, let me describe both of these in terms of what we've just been doing. You can look some of these up online, or you can even take a road trip to go look at them. So I'll start with the solar chimney. The solar chimney is related to the Christmas pyramid that I had just been describing. what you have is a very tall chimney, okay, and there is a canopy, and I'll just say it's open to airflow. So this is at ground level, this canopy here, and this chimney pierces or is connected to the air underneath the canopy. So it's open to the air right here. And how does it work? Well, this is a transparent canopy. You have solar radiation coming in here. Okay. And goes through the canopy, heats the air underneath, and because there's hotter air underneath now and colder air at the top, you get a chimney effect and you get a convection current. So down here you have TH, up here you have TC, therefore you get convection coming in all the way up. And if you can mount some turbines, say, in the chimney or conceivably underneath here, around it, underneath, you're just going to get the turbines to spin by that airflow. You're generating a wind up here. So is this a heat engine? Yes, it's a heat engine. What is the maximum possible efficiency of this heat engine? So 1 minus Tc over Th. Now this is going to be a pretty small temperature difference because you're up 50 meters, 100 meters, however tall you make this chimney. And because the air is always being replenished, in the sides, it can't become that sweltering hot under here. Okay, so the efficiency, if you make up some numbers, you're just going to have a few degrees Celsius difference here. This efficiency is going to be constrained by this law. Okay. Now, what about QH? Well, we know that the maximum amount of energy would be the solar energy that came through here. So we would have using the solar constant, let's write this out. So we talked about the solar constant, 1,340 watts per meter squared. So we use the solar constant, and then we would have QH would be equal to I times A, where A would be the total surface area, total surface area in square meters. And then let's see what we would have here. W would be E times QH. So this would be the power that you get out would be E times QH. So right here with these parameters, you have the absolute maximum that can conceivably be obtained from this. So your QH is the solar constant. Let's go ahead and write it out. 1,340 watts per square meter. A is just the area here, okay? So I'll just write area A right here, that big square. And then, so this is just the definition of efficiency, so I just solve for work. But of course, the efficiency maximum is the Carnot efficiency right here. So yeah, if you were designing one of these things and you get a hold of these parameters, you would have the maximum work. Who knows how much you'd really get? Some fraction of that even. But that would be the constraint based on the laws of nature, how much something like this could conceivably deliver. Okay, my other example, the solar thermal power plant. I'll erase these, even though I may need them again. So solar thermal in different forms. You can look. Kalinga has one for oil recovery or something like that. Yvonne Pa, that's somewhere on the way to Vegas. I think it's in Nevada. There are other ones, but you can look these things up. There, the idea is that you've got the incoming rays, so here's our incoming rays of light, and there is what's called a heliostat mounted on the ground here. It's a mirror that reflects the rays of the sun to a central tower. Central tower. So there's a central tower, and on top of it there's some drum up here. And we've got reflection. And in fact, those are called heliostats. They actually track the sun. So as the sun crosses the sky, these things change their orientation, so they're always reflecting to the central tower. And there's a whole field of these, bigger than a football field, a whole field of these mirrors. So they're called heliostat. Mirror, right? Whole field of these. You look this up, you can get some good images of what's actually going on there. So what's happening is you're concentrating the sunlight from many acres of mirrors right on this central tower. So there's a salt or some kind of liquid here. I think that's a molten salt. It gets enormously hot, and I'll start with that molten salt in there. You come down to a tank. Okay. That stores the salt at a high temperature, and yeah, you guessed it, this goes to a powerhouse. I'll just write power house, and then this, generate energy, so work, and then there is molten salt at a lower temperature, at which point it cycles back up the tower. So now I can draw some arrows. Right. We're going down here, up into the hot tank, into the engine. We're getting work out into the colder tank. And there you have it. So you could look one of these up. They're pretty interesting. Whole field of these mirrors. And again, you can take the solar constant times the square meters of mirrors in that field to give you your QH. Okay. And then if you know the difference in these temperatures, you can get the maximum conceivable efficiency of a system like this. So these are working with very high temperatures and good temperature differences. But yeah, so the analysis of this, and again, I wouldn't say there aren't fudge factors, but there are just factors of how efficient even these mirrors are and so forth. This is the absolute maximum amount of energy that's hitting this drum up here. Good, but the point is the analysis of these two solar thermal type of plants doesn't require any more than what we talked about today. Okay, I think that's enough for the day. Yeah, I'm going to put a homework assignment up. Next time, I think we'll do a homework assignment review on the board after I read all the emails. So what did I have here? We have homework number 7. These are from chapter 19. Chapter 19, 27 and 28. 42, oops, didn't write 28, 27, 28, 42, and 70. I think this is the interesting power plant one with the river cooling. Okay, good. See you guys next time.